In this video, we're going to be starting our conversation that's going to lead to actually reaction rates and things like that. But we're going to start off with heat of reactions. Heat of reactions, which is represented by a delta H with the subscript Rxn, which stands for reactions. The heat of the reaction, which is also known as the enthalpy of reaction, has units of a kilojoule per mole. It is the change in enthalpy or heat of a chemical reaction that occurs at constant pressure. It is a thermodynamic unit of measurement useful for calculating the amount of energy per mole either released or produced during a reaction. So it is that measure of energy that is released or consumed or produced during a reaction. It could either be released or produced. It could also be consumed or used. So it's the change in heat of a reaction. Since enthalpy is derived from pressure and volume enthalpy is derived from pressure, volume, and internal energy. The equation for our delta H of reaction can be seen as Q divided by N of reaction. Q, which is heat, which is going to be usually in kilojoules, is usually figured out during an experimental process, and N is the moles of reactants in that experimental process. So the heat of reaction is telling us how much heat is released per mole. A thermochemical equation is a balanced chemical reaction that uses the amount of heat that is produced or consumed during the reaction. So it's a chemical reaction. So say that we're going to talk about the combustion of propane, and we were told that the amount of energy released was negative 2,220 kilojoules per mole. Well, I could create a thermochemical equation by writing out that combustion reaction, and notice that I put plus 2,220 kilojoules. The reason why I put that plus sign is that since my delta H of reaction is negative, that means that energy is released, so it is a reactant. So it is a product. I could also say that I could also put plus heat. So either way, I'm saying that energy is being released. So again, that negative sign with delta H of reaction says that this reaction is exothermic. Energy is being produced. Energy being produced means that the energy or heat is a product. If we were to flip this reaction around, my delta H would then be positive, which means that it would be an endothermic reaction. And that means that my heat would be a product, so it would be on the other side. So depending on what the sign of that delta H is, we could either have that as a product or a reactant. So let's go ahead and look at this example. What is the value for our delta H of reaction for the following reactant if 88 kilojoules of energy is released when 35.2 liters of nitrogen monoxide reacts at STP? So we're going to go ahead and solve this problem on our next screen. All right, so here we have on our example that we're going to be looking at first. Now, one of the things that I want us to remember is our equation for our delta H of reaction that we have. We have that delta H of reaction is equal to Q divided by the moles of the reaction or the reactant. So what we're looking at. So we want to know what is the value of delta H of reaction of the following reaction if 88 kilojoules of energy is released when 35.2 liters of nitrogen monoxide reacts. So we know Q. We are told in this problem that Q is equal, if it's released, it's negative. We are told that Q equals negative 88 kilojoules. What that means is we need to find N of reaction. This is our unknown. And we're going to be able to find it by using the fact that we have 35.2 liters of nitrogen monoxide at STP. So we need to somehow get our 35.2 liters of nitrogen monoxide and get that into moles. So this is what we're going to do. Knowing that we have 35.2 liters of nitrogen monoxide, since this equation is at STP, we can use our formula and our known that says at 22.4 liters is 1 mole. But we want to know how much is for this entire reaction, not just this. And in this reaction, what we have is we have 2 moles of nitrogen monoxide for every 1 mole of reaction. So we want to make sure that we include that. And that's from this balanced reaction. So we have 1 mole of this reaction, or one kind of unit of this reaction. And there are 2 moles for that. So we want to make sure that we include that in there. And if we solve this, what we get is we get 0.786 mole of the reaction. So now what we can do, now that we have everything, we can plug this into our delta H. So we have delta H of our reaction is equal to negative 88 kilojoules divided by 0.786 moles of reaction. And so what you end up getting is you get negative 112 kilojoules per mole. Now, since this is negative, if I wanted to, I could plug this into my equation and create a thermochemical equation with this by putting plus 112 kilojoules, because for this reaction, I would release 112 kilojoules because that's negative. All right, we also have another problem that we're going to be doing here in just a second. So we're given a chemical reaction, and we're told that our delta H of reaction is a negative 26.74 kilojoules per mole. So again, that would be an exothermic reaction, and that would mean that this delta H, or this heat, would be a product. So we have 2 things we want to figure out. The first one is how many liters of carbon monoxide were consumed at STP if 88.5 kilojoules of energy is released. Then, how much energy is released if 30.0 grams of iron were formed? So kind of a 2 parts, and we'll solve these on the next screen. All right, so here's our next problem. So we're going to have 2 steps. These are both going to be some dimensional analysis type problems. So let's look at A. A says how many liters of carbon monoxide were consumed at STP if 88.5 kilojoules of energy were released. Well, we know a little bit. We know that if 3 moles of carbon monoxide are consumed, this is how much will be released. So now we're going to be using this value to kind of move backwards. So we know that 88.5 kilojoules of energy is released. I'm going to go ahead and put a negative because remember that's going to be an exothermic reaction. Now I need to get rid of my kilojoules, and I'm going to be using my delta H of reaction. So I'm going to put negative 26.74 kilojoules over 1 mole of my reaction. Now we want to know a little bit about carbon monoxide. Now in this reaction, in 1 mole of my reaction, 3 moles of carbon monoxide are consumed. So I'm going to go ahead and I'm going to put that in here. For every 1 mole of reaction, I'm going to have 3 moles of carbon monoxide consumed. Now the last thing I want to do is I want to get this to liters. And again, since this equation is at STP, we can use 1 mole is equal to 22.4 liters of carbon dioxide. Cancel out all of my units, multiply the top, divide by the bottom, and I'm going to get 222 liters of carbon monoxide. So that is my reaction for A. Let's go ahead and look at B. We're going to do something similar, but we want to know how much energy is released if 30 grams of iron were formed. So we know that this much energy will be released if 2 moles of it were formed, but how much with 30 grams? So starting off with 30 grams of iron, we need to convert this into moles. And we can use that using our molar mass, so 55.85 grams of iron over 1 mole of iron. And there are going to be 2 moles of iron for every 1 mole of this reaction. And now we could figure out the energy by plugging in that our 1 mole is equal to negative 26.74 kilojoules of energy. So I can go ahead and cross out those. So again, I converted my grams into moles. I use my mole of my product to the 1 mole of reaction. And then I use my delta H of reaction right here and plug that in. And I'm going to get negative 6.64 kilojoules will be released. So that's how much energy will be released if 30 grams of iron are produced. Enthalpy of formation, or delta H sub F. Enthalpy of formation is a measure of energy released or consumed when 1 mole of a substance is created under standard conditions from its pure elements. So what are our standard conditions? Well, here I have an example. So this would be my delta H of formation for carbon dioxide. Notice that it is being formed from its elemental parts. So we have solid carbon, and the elemental form of oxygen is O2, because remember, it is a diatomic. So delta state for elements in standard state, which is the same as standard conditions, are things like sodium, oxygen, bromine. And those all have a value of 0 kilojoules per mole. So if we know that those are 0, then we know that all the energy being associated with the reaction that we see above is going to be for the formation of carbon dioxide. So the delta H of formation value for compounds will usually be given by a problem or can be found on a table. And there is a table that is attached to your homework that you guys will see. So they can easily be looked up. So what is the difference between our delta H of formation and our delta H of reaction? Our delta H of formation is different from our delta H of reaction in that it describes the energy of a substance, so an individual substance, where the delta H of reaction will talk about an entire reaction. So how much energy is associated with a substance, a singular substance like carbon dioxide, versus maybe like the reaction of carbon dioxide with something else. So we have two different ideas, but we can use our delta H of formations to calculate our delta H of reactions. So we can use this equation right here, where our delta H of reactions can be calculated by taking our products, the sum of all of our products, finding the delta H of formation of those, and subtracting them from the reactants of all those individual delta H's. And I'll show you guys an example next. So we're going to be looking at this example, and we want to figure out the delta H of this reaction. So we have this reaction right here, and we're given some values in that table, our delta H of formation. So we're going to be using our delta H of formations to figure out our delta H of our reactions. Right, so here's our last problem. And in this problem, what we have is we are figuring out our delta H of reaction from some delta H's of formation. And we were given this equation. So we were given that our delta H of reaction is equal to the sum of N times our delta H of formations of our products minus the sum of N times our delta H of formations of our reactants. So the N represents moles, and our delta H's are going to be values that we have in the table. So let's go ahead and start kind of plugging things in. So we are given that our delta H of reaction is going to be equal to the sum of our products. So we want to look at our products first. So what I have here is I know that I'm going to have 2 moles. I'm going to multiply this by 2. Of our iron oxide, our iron 3 oxide, and that is negative 826 kilojoules per mole, plus my sulfur dioxide, and that's 4 moles of sulfur dioxide times this right here, which is going to be negative 297 kilojoules per mole. So that is going to be my products. So again, these values come from table. My 2 moles are going to be the coefficients that are out in front, so 2 and 4. So I'm going to add that all together, and then what I'm going to do is I'm going to subtract it from my reactants. Now, One thing that I want to point out is oxygen right here. Now notice that oxygen is not in our table. So you might think like, okay, how do I solve for that? This is in its standard condition. And because that's in standard condition, this is automatically 0. So things that are in their standard conditions, solid elements by themselves, like carbon solid, or anything that is a diatomic like that, will automatically be 0. So when I subtract my reactants, the only thing that I need to pay attention to is my iron sulfur. So I'm going to have 4 moles of that, and we are going to multiply that by negative 95 kilojoules per mole. Now be very careful when you're solving these because you want to pay attention to this negative. So this is going to be a large negative number minus a smaller negative number. So just pay attention to those negatives when you solve this. And from here, we get that our delta H of reaction is going to be a negative 2,460 kilojoules per mole. So this is an exothermic reaction, and that's how much energy it will release. So again, if you're asked to find the delta H of formation, you might have to use it for your delta H, if you're asked to find your delta H of reactions, you might have to use some delta H's of formations to solve that. And the one thing that you want to remember is make sure that you're paying attention to things that are in their standard state because those will be 0.